Welcome back, class, to another lesson in natural intelligence, the blueprint for AI. I am your instructor, your mentor, your host, your lead engineer, Norm. And remember, we are building a foundation of learning how our natural OS or our biological hardware works before we move over to the artificial side and learning about artificial intelligence. It's imperative that we dig a little bit deeper and learn how we learn before we are not able to anymore, before the AIs take that from us too. So, this course is designed to get you familiar with the way that the human brain works, the most powerful mechanism on the planet, maybe in the galaxy, who knows? And so before we start to understand the artificial intelligence, we need to dive in deeper on natural intelligence. Now, in lesson 5, we're jumping into learning about the knowledge graph, right? So your brain weaves every new piece of data into an interconnected web of prior knowledge called schemas. And modern AI does this as well, not exactly, but very similarly. And they use vectors or vector embeddings, I should say, in RAG or retrieval augmented generation. And we're going to talk about the relationship between how our brains do that and then relate that to how the AI is doing it. And before we get into the lesson, let's do a quick little recap here. So, in the last class, parallel processing, we learned that dual coding engages both the verbal and visual channels. Very important there that you're using both of these channels so that we can double the recall, makes learning twice as efficient, twice as optimal there. We also learned that the multimodal AI works in the same way. You have separate encoders fused into shared context, which allows an AI model like a ChatGPT, a Gemini, a Claude to be able to take video, audio, text, just about anything that you can think of that can be essentially converted down to vectors is able to be generated using these models, and in particular, the transformer architecture with the encoder and decoder setup that they have. We also learned about how to build a text to visual translation guide to activate both of those channels. So we breached a protocol. We were able to hack our brains by building these two particular activities through an architect activity and a builder activity to bypass some of the limitations of the parallel processing and get maximum use from it. A quick side note here, just to reinforce the parallel processing before we jump into the new lesson. Dual coding doubles our bandwidth, but something you have to think about is where does all of that information get stored? So now we've got, instead of 4 lanes, we have an 8-lane highway. All that information's coming into our brains. Well, where is it going? Well, that's going to lead us into what we're talking about tonight, and that is the knowledge graph. So today's mission is to weave new data into existing schemas. So we do have existing schemas that we develop over years. Think of these as essentially webs or networks of information, of learned data. And then we're going to connect every new concept to what you already know. And we're going to use analogies. We're going to use references, right? Relatability. That's the mission. How can we use those techniques to weave this new data into this existing schema so that it sticks? Because if it's not weaved into the network, into the web, it essentially gets deleted or it drifts off. And the mechanism here is the schema theory by Piaget. Sorry about that. Piaget and Bartlett. Okay. And the new data either fits existing schemas or forces them to restructure. right? So this is also how you can readapt or relearn or reprogram, I should say, is a better way of saying it. Reprogram your network or your schema if you need to. For example, if you need to break a habit, if you need to break a way of thinking, if you think that you can never learn anything new, that tech is too hard for you, that you can never learn how to program, you can never learn about AI, right? We need to deconstruct or essentially force the restructuring of your schema. And we'll talk about ways that we can do that. But there is a problem, right? The problem is that when you have these isolated facts, right? Just imagine you're sitting here, whether you're learning this material, you're maybe flipping through the different social media platforms. Maybe you have something going on in the background. You've got your family and friends and loved ones around you. You have all this data coming into you, to your brain. And a lot of it is isolated. A lot of it is kind of random. It's not connected to anything, just random fact type stuff. Well, the issue is that those isolated facts have no retrieval path, right? It's kind of in one ear, out the other. So no connections, no context, right? They get forgotten first, which again goes back to what we need to do in the mission. We need to make sure we're weaving information into the existing schema so that it's not just an isolated fact. Now, visualization for you to help wrap your mind around this, wrap your brain around it, literally. Okay. Just think about it. You have these isolated facts, these individual little dots here. Okay. These individual little dots. Now, this is information. Okay. Maybe it's in your mind for a moment, but it won't take too long for that information to disappear or eventually get overridden. Okay. And the reason is because it doesn't have this, what we have on the right-hand side, the schema, right? You can see the web network here with these little, what we call edges and nodes, essentially is what's going on here. And everything is connected, right? One fact is connected to another. It's almost like the 6 degrees of Kevin Bacon here, okay? Everything that you've learned that gets integrated into a schema can be traced back through the path of these different edges and nodes, right? And that's what makes the human network or the human brain's network so powerful and very efficient. And we try to replicate that in the artificial world. Now, how do schemas work? Okay, so just imagine here for a moment, you have books on the floor, right? Those books on the floor are these isolated facts, right? So go to an image here, books on the floor, isolated facts, right? They're not organized. They're just kind of thrown together. Maybe this looks like your room or your library. There's a time when I used to just stack my books up against like the back of my bed, like as a headboard. Yeah. But anyway, these are random isolated facts. And on the right-hand side, juxtaposed to that, you see very well organized system here. That's right. It's a system or network of books, right? You can maybe have genres, labels, categories, and whatnot. And so that's something that a schema can do for us here, right? We can have that organized library with shelves and cataloging so that we can make cross-referencing. We can look at same content and get that instant retrieval, right? In this case, the map matters more than the territory, right? Now, the mechanics, the way you think about it is that you've got assimilation. So new info fits existing schema, right? You think about the assimilation and how biology works and also how organisms work, right? If there's an existing structure, an existing network, an existing community, and you are thrown into that network, to that community, you have a choice. You can assimilate, right? Or quote unquote fit in, or you could run the risk of being ostracized or kicked out because you don't fit in, right? And the other option is what? You can restructure the community, you can restructure the schema and change it, right? You can kind of be that rebel, right? And so there are opportunities where isolated facts, isolated data, they do come into schemas, into our minds, and they reconstruct, they change the way we think. An idea changes everything we once thought was to be true, right? So assimilation can happen, but so can reconstruction. Accommodations, think about how a schema restructures to fit new info, right? Which we kind of just talked about. And then the hippocampus, right? The brain's search engine, right? This is how it indexes, or this is how our brain is able to index schemas across cortex. And the way I want you to think about this is it's like the search engine or Google of our brains, the hippocampus. And it's not an exact analogy, okay, or exact equivalency, but it is I think it's a useful analogy. And now the expertise equals denser, more interconnected schemas, right? So the more intelligence you have, the more expertise, the more practice you have with a particular topic or anything else that you're learning, you're going to have more dense, interconnected schemas. And this can work for you in your favor, but it also work against you for obvious reasons. If you have a very dense or thick belief and it's deeply woven into your psyche, it's very hard to get you to change your mind about something. It's very hard to get you to change your beliefs, right? And this is why a lot of people believe in the psychology world, when you start people young as children, you start giving them messaging. When you start the brain, when the mind is very young, very fresh, you can send that messaging, plant that seed, and continue to nurture that seed for years and decades. And before you know it, you have a very, very dense forest of a network. Now, the bridge here to AI, let's talk about the bridge. You have vector embeddings and RAG, or retrieval augmented generation. Now, let's talk a little bit about here about how the two relate. So with storage, we want to think about how you have storage, which is, again, just the holding of the knowledge. It's not necessarily memory yet, but it's a storehouse. Okay, so this is going to be knowledge in semantic schemas. And then storage for our AI are going to be vectors in high dimensional spaces. All right, we call these vector databases or vector stores for AI. Now, the indexing is handled by the hippocampus. It indexes by meaning. Essentially, it categorizes relevant terms, or it provides context for us. In AI, we have indexing through a multitude of ways, but one of them is cosine similarity clusters, which are essentially ways to group similar concepts together, right? And this is all math, okay? Math and a little bit of probability, but it's still able to, by converting text into numbers, or what we call vectors, able to look at a vector and see if there's a similarity in one vector array to another vector array, right? And that creates a cluster or a category. Now, retrieval in the human brain, you have association, you have concepts, they activate each other. Again, it's kind of this bucket of concepts. And then retrieval, very similarly, works with a RAG, or retrieval augmented generated query, from that vector DB, that storehouse of vectors for context. This is essentially when an AI goes to a bucket of information and the AI is saying, oh, I'm going to choose all these relevant topics because they are related or relevant to the prompt you gave me. And there's a little bag or a little location or vector database that has all of the data, but the data is labeled or indexed in a way to make it easy to find the context. Now, the weaknesses for both the human and the AI are that schemas can distort memory. And then for the AI, the embedding quality limits retrieval. So when you're embedding or essentially converting text to numbers, to floating point numbers, essentially what happens is that if you don't do it well, then you may lose the ability to have proper context and have good similarity search, right? So there's some restrictions on both sides. There's always going to be some limitations, and you just want to be able to acknowledge them and know ways to mitigate some of those. Now, the axiom here, embeddings position knowledge by meaning in math space. Schemas position knowledge by meaning in your cortex, right? Same architecture, different substrate. The argument could be made that the cortex is a math space as well, right? But just now we're getting into semantics a little bit, right? Now, let's do a little visual here to help you make sense of this. Now, just imagine these are vectors, right? And the way that the AI sees it. Now, the way we see it is that we see essentially these clusters, right? We see an animal cluster, we see a food cluster, and we see vehicle cluster. Now, within those clusters, you have these individual vectors or items that are indexed: a bus, truck, or car. You have pasta, sushi, and pizza for the food category, dog and wolf and cat, right? So this is a way, and this is how our brains process and organize data so that it's easier to retrieve. So when we see an animal, right, we have this knowledge store or this knowledge schema that has all these interconnected, isolated events that where we've seen a dog or we've seen a wolf or we've seen a cat, and we can quickly reference that particular vector or that particular memory in our cortex. Right? Same thing with the food, right? And also with the vehicles. So AI does this as well. Obviously, with AI, it's not words, they're going to be numbers. Okay. But what you can imagine is that you have one large array or an array bucket that is a particular cluster. And within those clusters, they're going to have individual vectors or attributes there that are going to be, again, selected based on the context of the prompt and the similarity or relevance. Now, how do we bypass this? How do we use this in our favor or prevent this from disrupting our learning? There's 4 ways we can do this. So we can build our schema using 1, connect before you collect. So all you need to think about is, ask, what do I already know? Okay. So before learning anything new, you want to find something that is similar, maybe not exactly, but you want it to be similar. And if you don't know what that is, if it's a very complex or very technical topic, okay, now you have tools. Now you do have large language models and AI to help you deduce that very high level technical information or maybe dense, deep information into something that's a little bit more related to something that you may know. Maybe athletics or sports very well. Maybe you can dissect a playbook like the best of them, but maybe trying to dissect an architecture of a AI system is a little bit more challenging for you. Well, maybe you can break that down and relate it to the X's and O's of a playbook. You can understand what happens when a play is called and where the different parts of the team or the different teammates are moving throughout the different parts of the field, where everybody's supposed to be in that particular play, right? There's a system to that. There's a flow, right? There's organization. And you can find ways to relate that by connecting again to information that you already know, making new information a little bit more relatable and understandable. Number 2, map the relationships. Okay. Don't just don't list facts. Okay. Draw connections. Right? Concept maps externalize your schema and reveal gaps. So again, you want to think about, how do you connect the dots here? It's not just these loose, isolated facts. How do they relate to one another? Then maybe you want to think about finding analogies. Another great way to again, find something that's relatable to you or something that's a little bit more easier to understand so you can map these new concepts onto familiar ones, right? And then 4, force the accommodation. So seek info that contradicts your schema. And this what this is going to do, right? This is essentially challenging, right? Challenging the existing way of thinking. And what this does is restructures or builds stronger knowledge graph. Okay. All right. So it's a way, if you think about it as exercising, right? Training your brain a little bit by tearing it down a little bit or pushing it to work a little bit harder, the same way we do our body and our muscles and our respiratory system in the gym. Now, here's an example. Let's say you want to learn a RAG system or how to build a RAG system, right? Now, RAG, again, we'll talk about what RAG is when we get to our AI section, our AI course. But just understand RAG is a way for you to impute context into a prompt that you're giving your large language model. Right? So it's a great way for you to get better context, better relevant results, and reduce hallucinations, reduce randomness in the way that your large language model performs with the prompt that you give it. So let's use this 4-step process that we just learned about on the previous slide. Let's apply this to this new learning, right? Again, let's say you're coming from a tech background, but you've never learned anything about RAG. Well, what do you know, right? Ask yourself the question, what do you already know? Well, I know about search engines. Okay. You know about Google. Okay. You know about Bing or DuckDuckGo. All right. And you know about these different search engines. And so you have at least a place to start. Okay. So you're connecting to known knowledge, right? Maybe you know about databases. Maybe you know about ChatGPT. Then the second step again is the map. Right? So now you're going to map, right? You're going to map, okay, oh, a query, when I search a search engine, that's querying or questioning or searching for information. Well, in a RAG system, you're doing that as well. You're querying a vector database. Okay. Now, you may know a little bit about databases or you may not, but you know where information is stored or information can be stored, right? So you can think of it as maybe a library or a place that you store items. Maybe if you're thinking about food, maybe a pantry. Okay. But you're querying or searching this thing, okay, that stores a bunch of information or stores something. Okay. Right? And this is how you map. You just go through each of the steps or each of the components of the particular concept you're learning about and try to find a way to relate it to, again, what you may know very familiar or may be very familiar to you. Number 3, analogies. Okay. With RAG, a librarian who pulls relevant books before answering. That's essentially what RAG is doing. So RAG, make the analogy, RAG is like a librarian. Now that, again, creates this visual for you. You understand what librarians do. That really does allow you to cement the knowledge or this information and make it stick. That this is now weaving it into your schema. And then 4, accommodate, right? Again, this is where we challenge our existing schema just a little bit to make room for new, more dense knowledge graphs. So again, you have an old belief, AI makes up answers. Okay, that's your old belief. This is maybe what you believed before you started taking this course or learning a little bit about AI or using it yourself, right? And now you have this updated belief that AI can actually ground answers in retrieved data, right? And this is what RAG does. RAG allows an AI to be grounded in relevant, real information, not generic information that it was trained on during its pre-training phase, right? So that's a quick example of how to apply those 4 steps. Now we're going to build a way or this map, right, for our schema graph here. Now our build objective for our architects and builders. The goal here is to map a single schema graph for a new topic, right? The new topic, you'll have nodes, which will be your concepts. Then you have edges, which will be the relationships or a way to connect those concepts. and this will connect new knowledge to what you already know. So that's the goal. How do you take something new and connect it to something you already know? Now, my architects, what you guys will be doing, you'll be designing a manual schema graph template, right? It'll be a reusable framework for mapping any new topic onto your existing knowledge. So again, just pretend you're Neo in the movie that we all like, right? Neo in the Matrix. You sit down in that chair, you get plugged up to the machine. The machine teaches you judo, it teaches you how to fly a helicopter, whatever it may be. You're designing that template now for schema redesign, where you're going to be able to manually hijack your schema and bring in new data using that template and learn about anything that you choose. My builders are going to be building a schema graph system prompt. So again, you're still focusing on prompting, right? We're not in code yet. We're still building our understanding up, especially for my non-tech folks out there. You guys aren't, have to worry about being overwhelmed by Python programming just yet. But you need to be thinking about ways to build or structure a system prompt where the AI is doing the lifting for you. It's going to extract the concepts, map the relationships, and outputs a structured knowledge graph, right? So how do you design a prompt and tell it to do that for you? Let's look at some of the requirements for each. So for my architects, you have the activate, right? Auditing prior knowledge. What do you already know? You have the extract, which is to identify 5 to 7 core principles, or excuse me, 5 to 7 core concepts or nodes from new materials. So again, identify some of these core ideas that you need to really master, and then be able to make relationships with them. And then connect, draw labeled edges, which are the relationships to these concepts. You're going to bridge, link 3+ new nodes to your existing knowledge graph. Okay, so this is, again, adding 3 new concepts here. And then test it, okay? Because we actually don't know if it works until we actually test it. So let's trace the retrieval, or see if you're able to recall any of this information, reach any node from any other in the more than 3 hops, okay? Now, an example of this, going back to RAG, where you have nodes, okay? You have query, embedding, vector database, retrieval, and generation, which bridges to context window and multimodal sections that we learned in the previous lessons, lesson 3 and lessons 4. Right? Now, for my builders, right? How are you guys going to be designing your system prompt, right? First, you need to think about extracting the 5 to 7 core concepts as named nodes, map those relationships as labeled edges, the causes, requirements, extends, identify prerequisite schemas the learner needs, and output a structured graph, mermaid, or JSON. I would lean towards JSON for my builders, just because we're going to be using JSONs a lot when we get into prompt engineering. So go ahead and get familiar with the JSONs, and then maybe have a summary here. You guys are stacking from lesson 2, high salience, lesson 3, chunking, lesson 4, text to visual, and lesson 5, our current schema graph lesson. All right, so some key takeaways here. What to remember from this lesson: your brain organizes knowledge into schemas, or these interconnected frameworks or networks, right? You can think of it like a huge web, right? That's not isolated files, right? No matter how much you think someone knows a whole bunch of random information, it's not random in their brain. It is connected to something. Number 2, schema integrated info. It encodes 3 times faster and retrieves far more reliably. Okay? So schemas are just better. Number 3, vector embeddings. This is our AI bridge. Vector embeddings equals schemas in a math space. RAG equals a hippocampal retrieval in silicon. Okay? So we have, again, the natural and the artificial here, bridging the two between a schema in our mind and a vector embedding in an AI system. Number 4, the map matters more than the territory. Organization beats volume. Don't think about ingesting or trying to get as much information, going down tutorial hell. Excuse my language. Don't go down that rabbit hole of trying to just learn and learn and learn and learn. What matters most is that you're able to make connections, right? You're able to map and index what you're learning so that it gets woven into that web or network of yours. And then number 5, the stack here is the high salience from lesson 2, the chunking strategies that we learned in lesson 3, the dual coding of both the verbal and the visual in lesson 4, and then finally our schema graph in 5. So again, we're building as we go. These are all all the way from lesson 1 through 5. We should be building on these axioms to help us learn new material because we're going to need them. We're going to need these axioms when we start looking at the AI modules and learning how AI works, right? We're going to need to practice this because for most of us, is going to be very new information. All right. So next class, we have class number 6. It is going to be the compression algorithm. We'll talk about compression. How do we break down the data that we have, make it a little bit smaller, understand and navigate error signals, active processing and loss functions. How do we keep the information there, allowing us to retrieve the correct information and not hallucinate, essentially. We'll talk about that in the next class. So go back to our building, rewind the video, look at our building objectives, try to build your system prompt for the builders, and for my architects, make sure you're trying to test out and design a template for you to help you learn anything, right? You guys should have these building objectives every class, right? You should be tacking them on to each one, trying to give you guys opportunities to practice what you're learning so that you're not just watching some random guy on YouTube, right? But anyways, as always, enjoyed serving you guys. Please do check in to the YouTube channel. Give me a like, go watch some of the other videos, and drop me some comments. Let me know how I can better serve you. Let me know what you want to learn. Let me know what you'd like me to break down for you. If you have any suggestions, let me know. I'm open, right? We're all in this together. We're trying to learn to be better creators and not just consumers, right? We want to be producers. And so this is my opportunity and my privilege to be able to producing some content for you guys. So hopefully it's helpful. Do share it with somebody else that you think might benefit from it. And until the next time, guys, take care. Class is dismissed. Peace.